Hey everybody, it's Mr. Francis, and welcome to Chapter 11. This unit, Chapter 11 and Chapter 12, are going to focus on first the elements, as they talk about atomic theory, and then Chapter 12 is going to focus on compounds and what's holding the atoms together. So we've talked about the atom previously. Ernest Rutherford put together this model for the atom that's kind of our basis and where we start. We've got a central nucleus, and as you can see, that central nucleus, positive charge, it has the protons and the charge, the neutrons, and the remainder of the atom has the electrons surrounding it. And this is what Rutherford's model looked like. Now again, Rutherford put together this model in 1911. Okay, so he pictured the electrons just kind of floating around the nucleus like you're seeing here. But one of the interesting aspects with Rutherford's atom, and as scientists started finding out more about the atom, is that elements gave off characteristic light. We know the visible spectrum. This is what we can see we can see on a daily basis. But you also see in the entire spectrum from gamma rays to radio waves, it's a very thin slice that's in there. Every light has two characteristics. One, the wavelength, and again, you think about that definition, you can see this, and a frequency. And you know the definition, you know the term frequency, that's nothing new for you. And we can relate the two, frequency and wavelength, to the speed of light. And what's nice about this equation is, since this is a constant, if you know wavelength, you can find frequency, and vice versa. If you know frequency, you can find wavelength. Light not only has this characteristic of a wavelength and a frequency, but it also has this characteristic of a particle, and those particles are called photons. And the photons can have different wavelengths, and they can be short, they can be long, and depending on their length, that's going to dictate the color of light that is emitted from the atom. And they do that by giving off energy. And I like that statement there. The energy is released in the form of that photon. So that color of light that we see that can be emitted from an atom is going to be based on energy. It's going to be based on that wavelength that we see here. And this kind of gives you some idea of, the idea of excited states. We're going to focus a lot of time on the ground state, which is the lowest energy state, the lowest possible energy for an atom with this. Within the atom, what we found is that their energy levels, and picture an energy level like the orbits around the moon, or around the sun, excuse me. Don't pay attention to the text messages. So picture like the orbits around the sun, each orbit being larger than the next, and the movement between the energy levels being the emission, of that light that we see for it. Hydrogen, really unique. One electron, but you can get these four very distinct lines with it that come with it. And again, those four distinct lines are all based on the movement of the energy levels and the electron and the photons from one energy level to the next. Energy levels are like steps going up a staircase. Okay, each step is an energy level with it. So that's the idea behind a quantized level. I'm not going to go through you can check out those. Niels Bohr is the one who proposed that we have these energy levels, and that the electrons, instead of what Rutherford said, the electrons actually exist in these energy levels surrounding the nucleus. And I like this statement here. They jump between levels by absorbing or emitting photons. So that movement, those lines that you see in a spectrum, come from the electrons moving from one energy level to the next. Bohr's model was a good start, but it has some errors. They're not circular. The orbits are not circular. They're actually spaces, and they can vary in shape around there. The model itself, as you can see here, hey, the electron's going to be in this certain area of space. And you look at the color here, the more dense the color, the more likely we're going to find that electron. They don't have sharp boundaries. We can have orbits that look like a sphere. we can have orbits that look like a pinched-in balloon that we're going to see here in a little bit. Hydrogen, the energy levels, again, very discrete, a lot like steps of a staircase. And that's how I want you to picture that with that. And then the movement, each energy level having a higher energy than the previous one. Those energy levels are then divided into sublevels. And you can see based on what the energy level is, that's going to be how many sublevels are in there. So we're in the first energy level. Hey, it has one sublevel. We're in the second, it has two. We go up to the fourth, it has 4 different sublevels that are in there. So the electrons can exist in these energy levels and then in the sublevels within the energy level themselves. And the sublevels have distinct shapes. The S sublevel, which is the easiest, the lowest energy, is shaped like a sphere. The P sublevel looks like a figure 8, looks like a pinched-in balloon. And then the shapes for what we call the D and the F are much different. Hydrogen only has 1 electron. We want to note that. But the atom, the hydrogen atom, you can put that electron in a 1s. You can put it in a higher energy level and a higher sublevel. We threw out Bohr's model because it didn't account for sublevels. It only accounted for the energy levels that you saw in there, in that atom itself. Every orbital can hold a maximum number of electrons. Pauli exclusion principle, a max of 2. So you go back, if we go back a couple slides here, each of these sublevels, if they're going to have a particular set of orbitals, each orbital can hold 2 electrons. So this P sublevel, the PX can hold 2, the PY can hold 2, the PZ can hold 2. So for 6, that gives you 6 total. Our modern model of the atom is based on an idea called the wave mechanical model. And you can see through each of these bullet points, they talk about the energy levels, they talk about the sublevels, and then within the sublevels, they talk about the orbitals. So pay attention, read through this as you're going through the unit, as you're working through the assignments in chapter 11. With the wave mechanical model, we put together what we call an electron configuration, an arrangement of the electrons in the atom. As you'll see from the examples, the electron configurations are actually fairly simple to note. There is an order to the madness. There is a filling order that is noted in the notes. So I want you to pay attention to that. And as you can see as we go from helium to lithium, one of the things you can note, you see these superscripts here. You add those up, they add up to the total number of electrons within an atom. And there is an order. Here we jump all the way to oxygen. Oxygen, if you go to the periodic table, has 8 total electrons. And look at how those 8 electrons are arranged in this configuration, this 1s2, 2s2, 2p4. And the same thing here with what we call this orbital diagram. This is, and I like this statement here, the last sublevel that's occupied for each of the atoms. And what you can do is you go left to right. Here's neon. Neon has 10 total electrons. You could say 1s2, 2s2. The last sublevel that gets filled is that 2p, and you can actually put 6 in there. When we talk about electrons, and this will come into play in chapter 12 quite a bit, we talk about the valence electrons. And I like the statement here, the outermost, the highest energy level electrons. So they're in that last energy level that gets filled, not sublevel, energy level. For this particular problem, I know they give the answer of 3. If you write out the configuration, you write out that diagram, you can see where those 3 electrons are for the cobalt. And again, this is the configurations just continuing on. And again, you've got the last sublevel that gets filled for each of these elements. And here's the other nice thing. look at, this is the fourth row in the periodic table. So look at how this is broken down. 4s1, 4s2, 4p, and then here's the 4p's. Hey, here's 1, 2, 3, and 4. And if you keep going down, each row in the periodic table is an energy level that we see with it. I like this filling order. Go left to right across this table. Find your element so that you can see what the last sublevel is that gets filled. So say it's this one in group 7. So that 5p would be the last sublevel that goes filled. And just go left to right across each one till you get to this point for the atom. The order here, when they talk about orbital filling, just gives you some hints for helping you write out configuration. So follow those steps with it. And then you can see a couple of examples in terms of electron configurations. We've talked about the periodic table previously. We know where all our metals are. We know where our nonmetals are. Here's a couple statements. Metals, they're going to lose electrons. They form these positive ions. We call those cations. The nonmetals, they gain electrons. They form these negative ions. We call those anions. The property ionization energy deals with the loss of those electrons. And again, you can see here, we don't really look at numbers. We focus more on trends with that property. And you can see this aspect here in terms of, as you go across the period, what happens to ionization energy. And the same thing as you go down a group, what happens to ionization energy. And you got a couple of concept questions here. Atomic size, same thing. You're going to see a very similar trend as you go across the period and as you go down a group. You see that increase with that. And again, we get the reasoning for this. So, if you have any questions, please give me a call. You've got my email, so I'll be willing to answer that for you. Take care.